Hello, everyone. My name is Odylo Costa. I'm a master student at UF, Universidade Federal Fluminense, under the supervision of Professor Bruno Santiago, also from UF, and Professor Sebastião Alvarez from Abdalla. I'm going to talk about the topic of my master thesis, that is unique ergodicity of the horocycle flow via hyperbolic dynamics. So, it's a classical result from the 70s, proven by Furstenberg, that the horocycle flow on the unit tangent bundle of a compact negatively curved surface is uniquely ergodic. Furstenberg's original proof was based on arguments from harmonic analysis, but during my master's studies, we decided to look at proof of a more general result due to Yves Coudin that has Furstenberg's theorem as a consequence. Coudin's theorem is the following. Let X be a compact metric space, G and H be two continuous flows on X. Suppose mu is a variable probability measure, invariant under both flows, and with full support. So, moreover, if we ask for the flows to satisfy this condition, that is a very common condition for the geodesic and the horocycle flows, and to ask the flow H to admit a dense orbit and the measure mu to satisfy a special disintegration condition, then the flow H is uniquely ergodic. So, what is this disintegration condition? First, given epsilon and x, define this set, that is the set of points that remains epsilon close to x under the iteration of the flow G to the past. Okay, so now the disintegration condition on mu starts with the following. For all x0 on x and for all epsilon greater than 0, there must exist a delta. Well, there must exist a delta such that whenever y, and we pick y inside of the set that remain epsilon close to x0 and the iteration of g, whenever y is not more far than delta from x0, then you do the following. You iterate x0 under the flow h for small time, say s smaller than 1, and look at the set of points that remains epsilon close to the point hx of x0. Then the iteration of the flow h beginning at the point y must intersect this set here in exactly one point. So it defines a function, and we ask for this function to be an homeomorphism. Okay. Moreover, we ask that in this coordinate system, the measure mu is, at least after renormalization, of the form of a product, where ds is the Lebesgue measure under the flow line, hs, and nu s are probability measures that depend measurably on s. Okay, so whenever the metric space is the unit tangent bundle of a closed surface with constant negative curvature, and G is the geodesic flow, H is the horocycle flow, and mu is the Liouville measure, then we get the special disintegration condition and the relation between the flows automatically. So we must ask whether there is a dense orbit condition satisfied for the flow H. Well, here is where we use hyperbolic dynamics. There is a theorem, Duplanche, from the 70s that states that a transitive nozzle flow on a closed Riemann manifold must satisfy one of the two conditions. Either it is the suspension of the diffeomorphism, or every stable and unstable leaf of the flow is dense on M. But now, in the constant negative curvature setting, the geodesic flow is a nozzle. Also, we already knew that the geodesic flow, the Liouville measure is invariant by the geodesic flow. But now, it being a nozzle, well, the geodesic flow must be transitive. So, it satisfies the hypothesis on the theorem of quantity, and since the geodesic flow cannot be a suspension, then every leaf of the stable foliation must be dense. Okay, but through a point x, the orbit of the horocycle flow coincides with the leaf through x of the stable foliation. Then this leaf being dense, we have that the horocycle flow is minimal, and in particular, there is a dense orbit. So from Coudin's theorems, we get that the horocycle flow is indeed uniquely ergodic on the unit tangent bundle, and we regain Furstenberg's theorem. Thank you for watching.